Hey, you know what's really cool? Calculus. That's right. Time to do some product and quotient rules. I do believe that's what's going on right now. So X17 means don't do 17, in case you didn't figure that out. So let's see. I think I'm on the right page and everything. All right, number one, it says compute the derivative of the given function by multiplying then differentiating, which we already know how to do in the last section, and then by using the product rule and make sure that they're the same. Okay, we can do that. So the first way would be f of x is equal to, let's see, first, outside, inside, last. I did a little combining terms on the fly there. So f prime of x would be equal to 4x plus 1. Okay, if we use the product rule, then f prime of x would be the derivative of the first times the second plus the first times the derivative of the second. And then I guess I just have to simplify this. So it looks like I got a 2x here plus another 2x here. Looks like I have minus 2 and plus, no, sorry, minus 1 and plus 2. It works. It better work because it's math. Math does not lie. Okay, so how about this one, f of x? If we FOIL this out, that's just the difference of two squares. Looks like this way is easier for sure. Okay, and then f prime of x, if we use the product rule, the derivative of the first times the second plus the first times the derivative of the second. I just take turns, right? And let's simplify that. So I got 2x cubed plus another 2x cubed. And then I've got minus 2x and a plus 2x, which cancel out, so all good. Number 5, find f prime of x. Now, I'm going to tell you something right now that's important for you now and in lots of other sections in our book. If you look in the back of the book, they're going to give you some kind of simplified version of the answer, usually. And for me and for the College Board, you do not have to simplify. Major caveat here. Sometimes it's really important to simplify because of what you need to do, because you're not done yet and simplifying has like a really big payoff. For example, if you're finding the second derivative of something, you need to simplify your first derivative before you do that, just because it's going to be easier and won't make you crazy. So that said, if the final answer is like some messy, unsimplified thing, and you don't have to do anything further with that, you can leave it. So the problem with that is you're not going to have the satisfaction always of being able to look in the back of the book and seeing exactly what the same answer is what you have. So what I would suggest, if I were you, I would every once in a while try to simplify one of these answers and get it to match up to the back of the book. And if you're scoring hits doing that, you can be pretty confident. You can also look at the videos. In my videos, I'll leave things unsimplified, so you can check against that. All right, number 5. Derivative of the first. Plus the first. I think I never said this. So the derivative of the first times the second plus the first times the derivative of the second. Right? The first, something's wrong there. Oh, I wrote the wrong thing here. If I saw the same thing showing up there, and that can't be right. So and spot check what your answers look like. Try to be good. Better than me, maybe. Okay, and I'm not gonna, I mean, you could simplify that some and whatever. I got better things to do. I'm sure you do too. Okay, so here the derivative of the first is 3x squared plus 14x times the second plus the first times the derivative of the second. Oh, that should have been minus. There. You want to simplify that? Go ahead, be my guest. And f prime of x for number 9, the derivative of the first is 1. I think that if you're really like super on top of things, number 9, that's actually the factored version of the difference of two cubes. So, you know, if you spot that, that's just x cubed minus 8, and it's a lot easier if you see that. So the derivative's 3x squared. But if you didn't see that, then that's got to be the same as, so kind of doing it like we did 1 and 3. Let's see if we can get it to match up. Derivative of the first is just 1 times x squared plus 2x plus 4 plus the first times the derivative of the second. All right, so is that the same as that? Well, we could do a quick bit. Let's just choose this to be the one that we spot check. Foiling this out, I got 2x squared. Let's see, minus 4 plus 2, that's minus 2x, and then minus 4. So sure enough, plus 2x minus 2x plus 4 minus 4, x squared, 2x squared. So that checks out. Great. Find dy dx at x equals 1 for the next few problems. So first thing I'm going to do is, oh, we don't have this, never mind, we can't do that yet. I was going to use a rule that you guys don't know yet. JK. So dy dx is equal to, okay, quotient rule. So you said this a whole bunch of times. Maybe it's starting to get imprinted onto your formidable brain. So let's see, low, d high, but the high is just a constant, so d high is actually 0. Derivative of 1 is 0, minus high d low over low low. Okay. So plugging 1 into this, so dy dx at x equals 1 is, that's 0, that's negative 5, nowhere to plug anything in, and then plugging 1 in here, we get 5 minus 2, so that looks like negative 5/4. Looks like the answer. I'm going to flip my answer key open to the answers to make sure I don't tell you anything that is untrue. That is true. And then same directions for number 13. That is, let's see, dy dx is going to be low d high minus high d low over low low. All right, and then dy dx at x equals 1 is, you want to simplify this first. You could. You can just plug the 1 into this, whatever you want to do. It looks like this does clean up considerably, that this, you got 2x here minus 2x, so the x's cancel on the top, and I got 6 plus 2, so it's like 8 over that. So 8 over, and then plugging 1 into this, 1 plus 3 is 4, squared is 16, which reduces to 1/2, which is not the correct answer. So let's see what I did wrong. What did I mess up? Oh, this is just a plus 1 here. I don't know why. That 2 messed me up. So that is 7/16, which most of the time does not reduce to anything. Sorry about that. All right, number 15, same deal. Ooh, okay, so there's a couple of different ways you could go here with this one. The best way to go, in my opinion, is if you look at that first piece, the 3x plus 2 all over x, you can divide through by that monomial. We talked about that in the last section, and turn that into 3 plus 2x to the negative 1. If you do that, what that means is you don't have to use the quotient rule. If you didn't see that, then it's a little bit tricky because you really have to juggle two rules at the same time, which is something that we should be able to do. We want to be able to do, and I think that I'll leave talking about that more until I make the video for the evens, because number 16, I think you cannot avoid it. So this one, I'm just going to take the easy way here and not have to do the quotient rule. Alright, so dy dx is derivative of the first, which is negative 2x to the negative 2 times the second plus the first times the derivative of the second. And I'm plugging 1 in. So let's see, that's just negative 2 times 2 plus 5 times negative 5. Oop, 17, x 17, I'm not supposed to do that. 19. I think the heads up here, if you're watching this before you get to the evens, we should also have said on the pacing guide, it should say x18 for the evens also. It's just those graphing utility things. We're not interested in that right now. All right, these problems I like a lot. 19, 21. Actually, the rest of these are all pretty great. So 19, find g prime of 4 given that f of 4 is 3 and f prime of 4 is negative 5. Okay, so what? We want to find g prime of 4. So g of x is equal to the square root of x times f of x. So what's g prime of x? Well, I have to do the product rule on this. This is x to the 1/2, so the derivative of the first times the second plus the first times the derivative of the second. Now, I don't know what the f function is. I don't know what the f function is, so that just is left like that. And if you look at that, well, like, how the heck are we supposed to get an answer for this? Like, they asked us for what's g prime of 4. Well, I think if I plug 4 in, I think hopefully I know what all these things are. So let's plug 4 in carefully. Not trying to do too much in this step right here. I'm just going to plug the 4 in and rewrite. Alright, so let's see what we can do here. 4 to the negative 1/2. 4 to the 1/2 is 2, and the negative sign flips it over. So that's 1/4. When I multiply this 1/2, this is 1/2, times f of 4. And if you look in the problem, it actually told us f of 4 is 3. Okay? The square root of 4 is 2, times f prime of 4 is negative 5. And that's it, people. So I got 3/4 minus 10, or what is that? Negative 37/4, I suppose. Number 19, B. So now g of x is equal to f of x over x. So I just cancel the x's out, and it's just equal to f. Just kidding, this is an x inside of a function. You cannot do that. So if you want the derivative, got to use the quotient rule. Low d high minus high, d low is just 1 over low, low. Alright, so g prime of 4, same deal. I'm just going to write that out. 4 times f prime of 4 minus f of 4 all over 4 squared. So that's 4 times f prime of 4, was that 3? No, negative 5 minus f of 4 is 3 over 16. Boom. That's it. '21, same kind of thing. Oh, except it's got 4 parts. Great, because I love calculus. Let's see. Here I've got part A. Big F of x is equal to that. So f prime of x is equal to 5 times f prime of x. The rule for if there's a constant multiple and you take the derivative, the constant multiple just stays there. Just like the derivative of 5x is just 5, because the derivative of x is 1. Okay, and then we want to find f prime of 2. And f prime of 2, little f prime of 2 is 4. And g prime of 2 is negative 5. 20 minus 10 is 10 most of the time. B. This time, big F is f of x minus 3g of x. So same thing, f prime of x is just f prime, little f prime, minus 3g prime of x. So f prime of 2 is f prime of 2, little f prime of 2, that is. F prime of 2 was that 4, I believe, yep, and minus 3 times g prime of 2 was the negative 5. So that looks like it's going to be 19. Part C. This time, big F is f of x times g of x. So this is just sort of like a generic product rule problem, right? Oops, sorry, that's what f of x is. And then f prime of x, derivative of the first times the second plus the first times the derivative of the second. And f, big F prime of 2 let's see what we got here. I'll try to keep everything straight. This is 4 times g of 2 is 1 times f of 2 is negative 1, and g prime of 2 is negative 5. And that's 4 plus 5 is 9. Good. And the last one of these is just a generic quotient rule. So the derivative of that, low, d high, minus high, d low, over low. I don't know why I put an equal sign there, because I need to indicate that I'm not doing with x anymore. Now I'm going to plug a 2 in. So, oh boy, this is so fun to write this out many times. I bet you're, are you too lazy to do this? Maybe you're too weak. Can't handle it. I bet you can. It's the right way to do it. Write stuff out. Don't try to be a hero. G of 2 is 1. F prime of 2 is 4. F of 2 is negative 1. G prime of 2 is negative 5. G of 2 is 1 squared. So 4 minus 5 over 1 is at negative 1. Yep. Right. Last 3. These are the thinkiest problems of this set, I think. So find all values of x at which the tangent line to the given curve satisfies the stated property. So we got y equals x squared minus 1 over x plus 2. And before I even start thinking about this, you know we're going to have to find the derivative, so I'm just going to do that. Let's see, so low d high minus high d low is 1 over low. Okay, now we're looking for x values where the tangent line is horizontal. What does that mean for the tangent line to be horizontal? If the tangent line is horizontal, that's because the slope is 0. And if the slope is 0, that means the same as the derivative is 0. So I have the derivative here. The tangent line is going to be horizontal when this is equal to 0. And I'll tell you something special about fractions that I bet you already know. That if you want a fraction to be equal to 0, the only way that can happen is if the top, and only the top, is equal to 0. So I need the top of this to be equal to 0. So this is a case where I'm going to simplify this now because I want to do some more work with it. So dy dx equals 0 when this, which is 2x squared minus x squared, 2x plus 1. So dy dx is equal to 0 when the top of this is equal to 0. And hey, that looks like a game that I know how to play. So dy dx is equal to 0. The slope of the tangent line of this thing has is horizontal when x equals negative 1. No, that is not correct. What did I do wrong? Let's see. Messed something up. Oh, I know what I messed up. So here, when I was simplifying this, do you know what 2 times 2 is? It's not 2, it's 4. So that just changes the last step here. So by like very small amount of inspection, that does not factor. So that means the x values must be quadratic formula, the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. So that's x equals negative 2. This is square root of 12 plus or minus. So I divided a 2 out there. So that's at those x values, that's where the tangent lines are horizontal. And yep, that's the truth. All right, quadratic formula, it's a thing. The tangent line is parallel to the line y equals x when, oh, instead of reading to you the book, I was reading the wrong thing there, sorry. 25, we have this. Before I even read the rest of it, I'm going to throw down derivative. Low d high minus high d low. Oops, high. Let me check that. Low d high minus high d low. Okay, I'm good now. Over low, low. I'm going to simplify that because I think there's stuff we're going to do with it. I'm going to be more careful this time, try not to make a mistake. 2x squared minus x squared. And I've got a 2x. No, x is back here. Minus 1 over x plus 1. There is not any benefit to multiplying that out. If you have things in factored form, that's good. They're better that way. So don't go foiling stuff out unless you're looking to combine terms like this. All right, so what do we want here? We want it to be parallel to the line y equals x. Well, the line y equals x has a slope of 1. So that means I want places where the slope, this, is equal to 1. All right, let's see if I can do that. So I'm just going to say this in words. Parallel to y equals x when dy dx equals 1. So there's dy dx, x squared plus 2x minus 1 over x plus 1 squared equals 1. And multiply that up to the other side. Looks like in this case it might benefit me to FOIL that out. So multiplying that up here, x squared plus 2x plus 1, those cancel, and I get negative 1 equals 1. What does that mean? Negative 1 does not equal positive 1. So what does that mean? Well, it means there aren't any x values that could make this equation true. This equation is always false. It reduces to something that is just permanently false. Can't pick any x values, going to fix that. So this is a case where we say there are no solutions to this equation, or maybe to answer a little bit more directly this question, no such x values where the tangent line is parallel to y equals x. Sorry, there just aren't any. Doesn't always work out. Let's see if I can squeeze 27 in here. All right. Another one like this. So, oh, this is a little trickier. Oh dear, I wonder if we can fix this. Fit this one in here. I'm going to make a little sketch of this one because I think that'll help you understand the setup here. So first of all, what does 1 over x plus 4 look like? It's got a vertical asymptote at x equals 4, and then it's just the inverse graph like this. And what they're asking us to do is try to find the x values where the tangent line to this passes through the origin. So if I make a dot here, can you take a second and look at that? Can you see if there are any x values, kind of like see about where they are? Here's one way to visualize like tangent lines. If you could imagine that these, we're looking down and this is like a map, and the graph here, these are like roads. And imagine a tiny, tiny little car that's driving along the road. Now imagine that that tiny, tiny little car has tiny, tiny little headlights, but they're really bright. And when that little tiny car is driving along that road, its headlights shine out in a straight line right in front of where the car is. Well, that's the tangent line. That line that the lights make, that's the tangent line. So as the car is driving along here, I feel like this pen is much too big for demonstrating this tiny, delicate little car headlights. As the car, looking desperately here for some other piece of equipment I can use. Well, here. I'm going to improvise some equipment here. So let's say, here's a little line on the edge of this piece of paper here. So how about that? So here, this is the direction. Oh, did I tell you, by the way, this tiny car, it also has, instead of having like the usual brake lights, like red lights that come on in the back of your car, there are also headlights in the back of it, and they're just as bright as the front ones. So that light that shines out the front of the car, it also shines out the back of the car. So as you're driving along, the car is turning and the lights, so it follows the road like this. So look at these tangent lines here. Do any of these go through the origin? Well, this is below the x-axis, and it's bending, it's pointing down, not very much, but it's pointing down, so it ain't going to get up to the origin there. So this keeps going like this. I didn't see anything that looked like it might hit the origin here. How about, let's go for a drive on this side. Going for a drive on the little road, the tiny, oh, look. So somewhere right about here, there's a tangent line that goes through the origin. Well, isn't that special? But how are we supposed to find the x value for this? Well, let's see. This takes a little bit of cleverness and ingenuity, let's say. So this right here is the origin. The coordinates of it are 0, 0. Everybody knows that. What about this point? Well, you've probably at some point or other in your math career said, you know what, that's just the generic point x, y. But instead of writing x comma y, I know what y is equal to. Y is equal to 1 over x plus 4. So if I have some generic point, like I don't know where this point is yet, I'm trying to figure out where it is. So that is a general sort of description in terms of x of any generic point on this function, and including the one that might be here. Okay, so the other thing I'm going to do here real quick is find dy dx, which is low d high minus high d low over low low. Okay, so anywhere that you are on this, whatever the x value is, the slope has to be this. I mean, it's a derivative. That's what the derivative is. But for this particular spot, I know that the tangent line for this place that we're interested in, it also has to go through the origin. So the slope of this line is rise over run, right? So the slope here is x minus 0 over, rise over run, other way around, y minus y over x minus x. So I'm going to take the slope of that line, like old school slope, since it has to go through the origin, 0, 0, then I have 2 points. So I'm going to make the slope equal to the derivative, and that's going to give me an equation that I can solve. So what's the slope? Rise minus 0 over run, x minus 0, is equal to dy dx, which is negative 1 over x plus 4 squared. Cool. And then I'm going to cross multiply, because I took algebra. I'm going to we have to decide where we want this negative to be. I'm going to let the negative belong to the 1 here at the top. and I'm going to cross multiply. So x plus 4 squared times 1 over x plus 4 is just x plus 4, because one of them cancels out. And then here, minus x. So it looks like we get 2x equals negative 4, x equals negative 2. And that looks about right for what our picture was here. It looks like it was somewhere in negative territory there. So that's good. That's a fun problem. I like that a lot. Just double check the answer here at x equals negative 2. Boom, that's it. See you later.